Hello guys, welcome back to another video on my channel. It's been a long time. I was busy with my exams. I was finishing up my master's program exams. And now I'm done with all the exams in my life. So with that, let's get started. We have before us this question from the Romanian Mathematical Magazine, this infinite sum over all integers of 1 over k to the fourth plus k squared plus 1. Well, the sum over integers is nice, but it's best to split it into a sum from 1 to infinity. How are we going to do that? Notice there's a symmetry. K goes to minus k, and this summand is invariant under such a transformation. So it's an even summand from on the negative axis and the positive axis. So we can split it from minus infinity to minus 1 and the zeroth term, and then from 1 to infinity. Because from the evenness of this summand, the one from minus infinity to minus 1 and the one from 1 to infinity will be the same. So we have twice sum from k equals 1 to infinity. And for the zeroth term, we just have 1 because k equals 0. You can plug k equals 0 in the denominator and you should get a 1. So that's why we have 2 times sum from 1 to infinity over k plus just the 1 zeroth term. Now we can simplify this denominator using a difference of squares. So we can write this as k squared plus 1 the whole squared. That will give us k to the fourth plus 2 times k squared plus 1. But we had a case 1 k squared here, not 2. So we can subtract that k squared. And notice that this is in the form of difference of squares. So we have a squared minus b squared, which we can write as a plus b times a minus b. So that's k squared plus k plus 1. That's one term, and the second term is k squared minus k plus 1. Everything else around it is the same. And now to simplify this further, we can factorize this by finding its roots. So the roots of the first term are minus 1 plus I square root 3 by 2 and minus 1 minus I square root 3 by 2. I'm going to call them k1 and k2. So I can write that first term, k squared plus k plus 1, as k minus k1 times k minus k2. That's for the first factor. For the second factor, the roots are 1 plus I square root 3 over 2 and 1 minus I square root 3 over 2. And we can write that term, k squared minus k plus 1, as k minus k3, the term times k minus k4. Noticing that k4 is just minus k1 and k3 is just minus k2. This is just purely from observing the roots. This is very useful because if we want to decompose this this summand term that's in the sum. The 1 is harmless, it's not doing anything. So the way to decompose this, now that we know the roots and the factorization, is to use partial fraction decomposition, because we had 1 over k squared plus k plus 1 times k squared minus k plus 1. That we can write that as a over k minus k1 plus b over k minus k2 plus c over k minus k3 plus d over k minus k4, where a, b, c, d are undetermined coefficients. And we can solve for those undetermined coefficients by cross multiplying on the right side. So we get a times k minus k2, k minus k3, k minus k4 plus b times k minus k1, k minus k3, k minus k4 plus c times k minus k1, k minus k2, k minus k4 plus d times k minus k1, k minus k2, k minus k3. All of that equaling the numerator of the left hand side, which is 1. And of course, you can expand each term in the bracket, gather the k cube terms, k squared terms, and the constant terms, and then sort of have 3 different equations. But that's not what we're going to do here. What I'm going to do is I'm going to instead plug in k equals k1 in this equation. When I do that, every term apart from the first one will cancel off. And then that's one equation. Second equation, k equals k2, k equals k3, k equals k4. I will have 4 equations here. If I do this individually, this is the Heaviside method of solving this. So for the first equation, I have a times k1 minus k2, k1 minus k3, k1 minus k4 equals 1. So we can do the algebra because we know what these k1, k2, k3, k4 are. Plug them in and we get a equals, simplify to e to the minus I pi over 6 over 2 square root 3. Similarly for b, instead of k1 we'll have to plug k2 now. Do the algebra, simplify that, and that gives us e to the I pi over 6 over 2 square root 3, essentially the complex conjugate of a. And c, doing the similar process with k3 will give us just minus b, and then observing just the pattern of what's going on with the complex conjugates, we get d is minus a. So we've determined what a, b, c, d are. Moving forward, we're also going to need this formula of the difference of digamma functions. So digamma of a plus 1 minus digamma of b plus 1 is sum from k equals 1 to infinity of 1 over b plus k minus 1 over a plus k. Because if you notice, when we plug the coefficient values in, I haven't plugged in for a and b, but we know what c and d are. They are dependent on a and b. We get the sum s equals 2 times sum from k equals 1 to infinity, a over k minus k1 plus b over k minus k2 minus b over k minus k3, because c was minus b and d was minus a. So minus a over k minus k4 plus 1. Now we can just use simply the difference of these digamma functions, but we have to notice that we have a minus a and minus b in these parameters here. So we have 2a. So we can take the a in common and with the 2. So we have 2a and then a difference of digammas. So digamma 1 minus k4 minus digamma 1 minus k1. Similarly, plus 2b, digamma 1 minus k3 minus digamma 1 minus k2. And again, add the 1. So notice this first term, digamma 1 minus k4 minus digamma 1 minus k1. k4 is minus k1, so we have digamma 1 plus k1 minus digamma 1 minus k1. Now what I'm going to do here is I'm going to add and subtract digamma of minus k1, because what that helps us do is we have digamma 1 plus k1 minus digamma of minus k1. We can use this first reflection formula on the digamma. Digamma 1 minus z minus digamma z equals pi cotangent pi z. In our case, z is just negative k1. So that gives us pi cotangent minus pi k1 from this first. And we're also adding the digamma of minus k1 minus digamma of 1 minus k1. To simplify that, we will use the recurrence relation on the digamma. Digamma of z plus 1 minus digamma of z is 1 over z. In our case, again, z is minus k1. So we get minus 1 over minus k1, which can be simplified to minus pi cotangent pi k1 plus 1 over k1, because the cotangent is an odd function and we have the minus minus becoming a plus. Similarly, we can simplify the second term to be a difference of digammas. Digamma 1 minus k3 minus digamma 1 minus k2 is k3 is minus k2. So digamma 1 plus k2 minus digamma 1 minus k2 gives us minus pi cotangent pi k2 plus 1 over k2. So plugging this in for those sums that we had, those infinite sums we had, s equals 2a 1 over k1 minus pi cotangent pi k1 plus 2b 1 over k2 minus pi cotangent pi k2 plus 1. Now plug everything in. Plug for A, plug for B, plug for K1 and K2. So let's first plug for A and B. We can plug K1, K2 later. So we have 2 over 2 square root 3 in bracket square root 3 over 2 minus I over 2. And we can plug for this K1. We can keep the cotangent K1 as it is for now. So minus 1 minus I square root 3 over 2 minus pi cotangent pi K1 plus 2 over 2 root 3 square root 3 over 2 plus I over 2. And then in this bracket, we have minus 1 plus I square root 3 over 2 minus pi cotangent pi K2 plus 1. We can simplify this product. So this term outside in this bracket, we can multiply with this first term. That just simply becomes, we have the outside factor 2 over 2 square root 3. And the inner terms simplify to minus square root 3 over 2 minus I over 2. And we can do that with the other term in the second cotangent. So which means this term in the bracket with this term, this first term with the cotangent. So we have 2 over 2 square root 3 minus square root 3 over 2 plus I over 2 plus 1. And then write the multiplication with the cotangent, so that we had this external bracket multiplying with the cotangent. So we have minus 2 pi over 2 square root 3 in bracket square root 3 over 2 minus I over 2. And cotangent of, now we can plug in for K1, minus pi over 2 plus I pi square root 3 over 2. And similarly, for the other cotangent, we get minus 2 pi over 2 root 3 in bracket square root 3 over 2 plus I over 2. Cotangent of minus pi over 2 minus I pi square root 3 over 2. We can use the complementary angle formula, that cotangent of pi over 2 minus z is just tan of z. And we can simplify. The terms in the bracket will just become minus 1. We had a plus 1 that was following us from the beginning. So minus 1 plus 1 plus, there's some terms that are going to survive. The imaginary terms are going to survive, but we'll write them all out for the cotangent. So 2 pi over 2 times square root 3 in bracket square root 3 over 2 minus I over 2. Instead of the cotangent, we have a tangent using this complementary angle formula. So tangent I pi square root 3 over 2 minus 2 pi over 2 root 3 in bracket square root 3 over 2 plus I over 2 tangent of I pi square root 3 over 2. So notice we would have a negative here. We use the fact that the cotangent is an odd function. So we have a minus that will cancel this minus to have instead of minus pi over 2, a pi over 2 minus I pi square root 3 over 2. That kills this minus from the first cotangent. So that's why we have a plus here. But for the second one, when we do that, we'd have pi over 2 minus of minus I, because this is cotangent. This is going to be pi over 2 plus I when we try to kill that minus by, removing the minus that's inside. And that gives us an additional minus sign because we have tangent of minus I pi square root 3 over 2, and tangent is odd. So we have to pull out another minus that will give us a minus. If you sit down and do this, you will understand what's going on. And then notice that the real parts here in this factor will go away and the ones will cancel. So we have minus pi I over square root 3, tangent of I pi square root 3 over 2. Then we can use just the relation between the circular trigonometric tangent and the hyperbolic tangent. So we have tan of iz is I times tanh of z. So we can just write this as I times tanh. So I and minus I will become a 1. So we have pi over square root 3 tanh of pi square root 3 over 2. And that's it. There's nothing else to be done. You can check this with Desmos or some calculator up to certain values. But this should be the closed form of the sum over all integers of 1 over k to the 4th plus k squared plus 1 is just pi over square root 3, tanh of pi square root 3 over 2. Let me know if any step here wasn't clear. I didn't want to waste too much time explaining the algebra, because the algebra is just elementary complex analysis with manipulations with reciprocal complex numbers and things like that. And the ideas are pretty simple. We're using complementary angles, partial fraction decompositions, um, factorizations of polynomials, and Digamma function and its properties, essentially, to simplify this question. The part here about the minus, I'm assuming you're familiar with the trigonometric manipulations of this kind, or we pull the minus out, or just variations of this complementary angle formula. But that's why I said, let me know by email if something wasn't clear. And yeah, that's it. Thanks for watching. Please like, share, and subscribe to my channel. And peace out. Keep doing math. See you in the next one.